Few events in the universe are as dramatic as the death of a star. Magnificent and incredibly beautiful nebulas emerge, they shine brightly, and depending on their distance from us, can even be visible from Earth during the day. Just think, in a single day, a supernova releases more energy than the Sun will in its entire lifetime. However, one of the biggest challenges in observing and studying supernovas is that, compared to other astrophysical phenomena like the life cycle of stars or galactic collisions, supernovas are fleeting events. Depending on the star undergoing the supernova, it might remain visible in the Earth's sky for only a few days to a few months. Moreover, observation can be complicated by other factors, such as interstellar dust that lies between us and the star, as well as the star's own distance from us. But before we dive into supernovas, let's take a look back at history. Before we understood that some stars end their lives in a magnificent explosion, people believed that supernovas were actually the birth of new stars in the night sky. Historical records, such as those from the year 185 AD, tell us that Chinese astronomers spotted a guest star in the night sky. This guest star remained visible for 8 months, shining brightly and displaying a variety of colors. What they witnessed was a supernova, or more accurately, a likely supernova. Another account of a probable supernova was documented by the astronomer Tycho Brahe. In his time, a new star appeared in the sky and outshone Jupiter for several days. This observation is particularly fascinating because Brahe lived during an era when people believed the heavens were immutable and eternal. Yet, there it was, the sky had changed. Supernovas are events of extreme energy, and we've faced significant challenges in comprehending the scale of this energy. To understand this, we need to know a few basic things about stars. Essentially, they're gigantic nuclear bombs, deriving their energy from nuclear fusion. This process happens when the cores of light atoms, like hydrogen, which has just one proton, combine to form heavier nuclei, such as helium, with 2 protons. This process also releases a considerable amount of energy, facilitating the fusion of more and more atomic nuclei. However, there's a special condition required for nuclear fusion to occur. Both temperature and pressure need to be extremely high. And guess where this ideal scenario is found? In the cores of stars, the real furnaces of the universe. Stars are massive accumulations of matter in a region of space where gravitational force pulls all this matter towards the center, increasing temperature and pressure. Stars are incredibly massive. To give you an idea, 99.9% of all the matter in the solar system is in the Sun. Everything else, Earth, the other planets, and even us, are essentially just ornaments. And what's most intriguing is that only a truly large star has what it takes to become a supernova. Gravity constantly draws all the star's matter to the center, heating it as a result. However, when a certain temperature and pressure are reached, nuclear fusion begins, generating a counterpressure to gravity and keeping the star stable. If gravity were the only force acting on a star, without any opposing force, all its matter would eventually be compacted into a small region at the center, and the star would likely become a black hole. Similarly, if gravity were absent and only the star's internal pressure were at play, it would eventually expand and disperse over such a large area that it would cease to be a star. Thus, it's crucial for a star's existence that these two forces are in balance. If either gravity or internal pressure begins to dominate, it signals that the star is nearing the end of its life. But don't forget, this internal pressure comes from nuclear fusion, and fusion requires fuel. Smaller stars, like our Sun, will continue fusing hydrogen into helium until their hydrogen supply runs out. When that happens, the internal pressure decreases, and the star literally shrinks a bit. However, during this shrinkage, gravity compresses the matter so much that it generates more pressure. Then, a new phase begins. The star has the necessary conditions to fuse helium into carbon and other heavier elements. But once the helium supply is depleted, the process repeats itself. As a star progresses in fusing elements on the periodic table, it reaches a limit. When stars like the Sun get to carbon and deplete their supply, gravity will never be able to generate enough internal pressure to continue fusion. There simply isn't enough mass. And that's essentially the end of the star, a quiet, undramatic end without an explosion. From the moment the fuel runs out, the Sun would become a white dwarf, supported only by the repulsive force between electrons, in a realm of atoms extremely close to one another. But what if, somehow, we could add more mass to the Sun, just to see what happens? In reality, there is a way for this to occur, leading us to type Ia supernovas. If a white dwarf has a companion star, which is common in many star systems, it could steal mass from its companion. This process would increase the mass of the white dwarf and, consequently, its gravitational force and internal pressure as well. This increase would continue until reaching a critical point where it would be possible to begin fusing carbon. But when the white dwarf reaches that point and starts the fusion of carbon, a surprise occurs. The fusion of carbon releases so much energy that the force of the fusion wins the battle against gravity, resulting in a massive explosion. This explosion ejects the star's mass into space and scatters all its elements across the void of the cosmos. This is known as a type Ia supernova, and it has a unique property due to the way it forms. The brightness of these supernovas is extremely consistent, making them valuable tools for astronomers to measure distances in the universe. For all astronomy enthusiasts and those curious about the universe, there's something truly fascinating about supernovas. These cosmic events are not just spectacular, they serve as a kind of universal lighthouse, helping us measure distances to other galaxies. Just imagine, all supernovas of a certain type emit, essentially, the same amount of light. This means that by observing a supernova of this type, we can use the amount of light that reaches Earth to calculate the distance to it. This method is an incredible tool for measuring distances between our galaxy and others, acting as a real universal ruler. But to truly appreciate the beauty and complexity of supernovas, it's essential to understand the dance of forces acting within a star. On one side, we have gravity trying to pull everything toward the center, on the other, nuclear fusion, striving to expand the star. When the fuel runs out, gravity begins to prevail, but then pressure increases, and a new element starts to fuse. This delicate balance between gravity and fusion is crucial for understanding supernovas, as it's when this balance is broken that the most massive stars meet their spectacular end in a supernova. In the most massive stars, the last element to be fused is iron. From that point on, the star finds itself at an impasse. Fusing elements heavier than iron consumes more energy than it releases, meaning the star cannot use iron as fuel. And when the fuel runs out, gravity wins the final battle. Atoms are compressed more and more, and the star begins to collapse. The core of the star reaches such a high density that protons and electrons combine to form neutrons. What remains is a compact core of neutrons, a neutron star. The extreme closeness of these neutrons generates a pressure opposite to gravity, preventing the core from collapsing further. This pressure, known as degeneracy pressure, is a somewhat complex quantum phenomenon but is crucial in preventing the star from collapsing completely. However, it's important to note that while the core has stopped compressing, the same does not apply to the rest of the star. This tale of the dramatic end of stars not only captures our imagination but also unveils the intricate tapestry of physical laws that govern our universe. By understanding these astronomical events, we get a little closer to uncovering the deepest secrets of the cosmos. And now, things start to become truly fascinating. The lower layers of a star continue to compress against the neutron core, which is extremely massive and compact. Picture this: a neutron star has roughly the same mass as the Sun but is confined to a space the size of a city. When the outer layers collide with this core, the impact is phenomenal, as if they were being bounced off a wall against which you throw a ball at 25% the speed of light. They react with an explosion of energy and are ejected into space. This is what we know as a Type II supernova. But, while supernovas mark the dramatic end of a massive star's life, that's not really the end of the story. Supernovas are the only environments in the universe where conditions are right to create elements heavier than iron, such as gold, lead, and uranium. Inside stars, most of the elements heavier than hydrogen are formed, but it's in supernovas that elements like gold and uranium are forged. And it doesn't stop there. When a supernova explodes, the remnants of the star are scattered across space, creating nebulas. These nebulas, filled with stellar dust, can eventually clump together to form new stars and solar systems. Nebulas are the nurseries of new stars. Our own Sun, for example, was formed from a nebula, as was the entire solar system. We exist here today because, at some point in history, one or more supernovas occurred, ejecting all the atoms that now make up our bodies, the bodies of those we love, and all the other things and forms of life around us. Supernovas are not just some of the most energetic events observed in the universe. They are also fundamental to the formation of life as we know it, and perhaps other forms of life scattered throughout the cosmos. In a way, you and I are partly the legacy of some of the greatest explosions our universe has ever seen.